There's 20 minutes for this talk, so I'm going to do a few things. One, I'm going to cut questions. If you want to talk about deep learning or ask questions about things that I'm kind of skipping over, more than happy to talk about it afterwards. I'm here till Saturday. Two, I'm going to skip most of the introduction stuff. I'm from Texas, went to Montreal, now I work north of New York. So with that, we're going to go into the crash course. I also cut convolution, so if you want to talk about that, meet up with me afterwards. Okay, so we're talking about deep learning. Where does deep learning fall on what I call the spectrum of automation? So during the scikit-learn tutorials, there's a lot of people asking about introspection. Deep learning kind of does away with most introspection. There are ways and methods to look deeply into your models, but it's very hard to do interpretable things. So I've built this handy automation spectrum that most people in this room probably immediately fundamentally disagree with, but that's okay. On the bottom left here, we have some packages in Python for doing this kind of stuff. We've got scikit-learn and Shogun and stats models and Patsy. And then kind of over on the right, we have a bunch of packages you might not have heard of. So Theano is kind of the, I would say it's the NumPy to most of the other libraries, scikit-learn. It's kind of the building block for all of these different packages. And the ones on the far right are all used to build deep neural networks, and they have various trade-offs. And packages that I work on, scikit-learn Theano, doesn't let you train at all. So if you just want to apply stuff, that's a nice option. Theano is also from Montreal, and David right here can also talk in detail about Theano. You're welcome. All right, so let's go over some basic anatomy. What is a neural network exactly? So we have some concept of some weights and biases. If you ever read about neural networks, we'll talk about weights and biases all the time. Sometimes we'll just say W and B. In any case, we start out, we just set the weights randomly. We morph, we set the biases at 0, we do some nonlinear functions, and then we say, okay, given that we took some input with some features and then tried to classify it, how wrong were we? Most of the time, random initialization. Very, 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 very wrong. So we have a method to take that error and say, well, I was wrong, but I can tell how I was wrong, and I can feed that information back through all of the little weights. So you can imagine it kind of like a sound engineer. If you didn't know anything about music, someone took you to a conference, sat you down in front of a mixing board with 1,000,000 knobs and said, make the band sound good. What would you do? You'd start tweaking knobs little by little. You wouldn't do big moves because that might be weird. You tweak them a little bit at a time, listen, tweak, listen, tweak, listen. So it's kind of similar. You need a lot of data. You need to probably have pretty complex input, but in return, you get a lot of very interesting behaviors. So you can also imagine that if you had the mixing board and someone came along and said, oh, well, this stuff kind of controls the bass, and this kind of controls the guitar, and this is kind of global, that would help you even more. So there are ways that I'm going to talk about in a few minutes to input your knowledge of the structure of your problem into a deep neural network. So I promised to talk about general guidelines. General guidelines, and this is the slap-worthy stuff. If people do deep learning, they might come slap me after. You pretty much want to use ReLU, rectified linear units. They're generally good, generally useful. Use them. Optimization-wise, there's a couple optimization methods you can use. You're going to have to Google these later. I'm not going to go into math and extreme details. Dropout is kind of the standard regularization for neural networks because neural networks are very, very, very good at overfitting a problem. And if you were at the scikit-learn tutorials, we talked at length about overfitting. If you're not familiar with machine learning, just know that neural networks are very complicated, and it would be very easy to make one band sound good, and the next band shows up, and they sound awful. So there's a great reference for initialization, which is important to neural networks. I'll just leave it to Google Plus to check that out. So here is one example neural network, and I'm going to kind of use this neural network to show off some of the things I want to talk about. Broadly, we have this neural network that has a special layer, we'll call it Z. You notice that it's smaller than the input and the output. So what we're trying to do here is we take some input, maybe it's an image, maybe it's a digit, and we're trying to compress it in some way, and then we're trying to reconstruct it from the compressed version. So what we believe is that if the compression is good, then things that are alike visually might be close together in Z space. It's similar to the concept of like neighbors, if you know about k-nearest neighbors. We want k-nearest neighbors or something like it to work well in the Z space. So you can imagine that's pretty hard, but luckily we can just make the green parts on either side deeper and deeper and deeper and deeper and deeper and deeper until it works. At least that's the theory. And so we call this encode decode, and it's very useful, and it shows up all over the place. So the network we just saw can also be represented by the X and the Z we see here. So those two tiny little lines can represent an arbitrary number of neural net layers. So if you see these diagrams in a paper, don't be fooled. We can also introduce side information, something called conditioning. If we know something about the digit in this case, we can use that to tell the network, hey, I want you to separate out style and class. So over on the left, we kind of just trained it, let it do its own thing. You can see it learn something called a smooth space. It's kind of blurring things together. There's parts in there where you get something that's not a digit at all. On the right, you see that we're varying Z, so we're moving around in this space, doing a bunch of stuff, but we're holding the class fixed, and it does not change class until we say, hey, okay, I want you to flip to a different class. So that means we're preserving style independently of class, and that's actually really powerful. So in the bottom right, the leftmost column is an input digit, and on the right, you can see holding Z fixed and flipping through the different classes. So we have 10 different possible classes. We can see that we can preserve style and flip between different types of digits. So you can imagine how this could be powerful. In general, this is a baby step towards encoding our knowledge. We know that you can write a 4 that's upright and a 4 that's slanted, and that's a 4 that's slanted is still a 4. We can encode that in the structure of the network. So in practice, conditioning is a very strong signal. We just saw something that part of the network is doing P of X hat given Z. That's the reconstruction piece. We saw that we learned something that might be more interesting if we included side information, Y, into the conditional probability we're trying to model. So we can use this to give control. We can also do it in the middle of the network to encode our knowledge about the type of data we want to work with. Classification is like a really, really strong form of this. Basically, we say we don't care about Z. We want right answers. And for you, this might be good enough. If you like to do pretty graphics, maybe not. So what do we mean when we say conditioning? Well, it's actually surprisingly straightforward. You can take your input features, make a representation of the label, perhaps with the scikit-learn label binarizer, concatenate those features together, and cram it through a couple layers of a neural network. After 2 or 3 layers, you can kind of guesstimate that things have mixed well enough that you can start trying to separate things out again. It's kind of a weird thing to say, but a lot of neural net research is pretty heuristic. The conditioning could also be reevaluated if you have some other indicator you want to use. So we talked about feed forward. Feed forward really doesn't make any assumptions about the relationship of your features. But we know that there's a lot of data in the world that has structure. So we want to encode that in the type of processing we do. The 2 main ways to do this are convolution and recurrence. I'm skipping convolution. Sorry, image processing people, and I'm going to discuss recurrence a little more. So basically, recurrence says we believe we have a sequence. So that means if we look at the probability of Y given the first thing, then we look at the probability of Y given the first thing, the second thing, then the probability of Y given the first thing, the second thing, the third thing, and so on and so forth. At some point, we believe we can model the probability of some tag given a sequence. And Y can also be a sequence, and I'll talk about that in a minute. If you're familiar with something called the HMM or the Kalman filter, you'll notice that looks a lot the same. Basically, we are not making something called the Markov assumption, so it should be more flexible, in return much more painful to use. And a Kalman filter is also similar, but we have to have someone really smart think really hard and do a state space model. In the RNN, we're trying to learn the state space naturally from data. Lots of power, lots of flexibility, Also quite nasty in practice. One additional thing that's pretty interesting about recurrent nets is you can use them to compress information. So this has been the recent rage in the last 2 years. Basically, you can take a sequence, run it through a recurrent neural network, and learn some state. At the very end of that sequence, the state that you have should encode some probability given everything before it. So what you believe is that your training procedure has learned what is important and what is not important about a sequence. So you might say, okay, well, I don't work with sine waves. I don't really care about sequences. But a lot of things are sequences. Sentences are a sequence. A dialogue between different people, either spoken or written, is a sequence. Sounds are obviously sequences. Videos are sequences. There's a huge number of sequences in the world. And so when you look at this as a potential way to map a sequence either to a label or to another sequence, you can really kind of start looking at weird things like automatic text-to-text translation or speech recognition or looking at an image and generating a caption. Some really, really kind of bizarre things, but it's all possible given enough data. So a little side note on recurrence. You want to be very careful when you initialize, and I'll link to code and a repo at the end of this. You're not meant to immediately just say, I get RNNs. You also want to use some fancy activations. They're very helpful for certain pathological problems in recurrent nets. But we can solve a lot of problems. Many to one to many, one to many to one to many, which is like a recurrent encode decode. So the network we saw before with the feed-forward layers to Z, now everything in between can be a recurrent neural net. So then we're learning a representation of a sequence that can be generated into something else. This is how the English to French thing works behind the scenes. One more thing we can do is we can take the outputs of neural networks and treat them as parameters to a probability distribution. This sounds insane, totally, absolutely insane. But it's incredibly powerful. With a recurrent neural network, it actually gives us a way to learn a dynamic distribution over time. So we can learn a Gaussian mixture model whose weights and means and variances and all this stuff change dynamically based on the input sequence. You can use this to do things like generate handwritten text. You can use this to do things like generate speech. It's incredibly powerful, incredibly complicated. So where is this actually used? I've talked about it a little bit. We use the convolution piece that I'm avoiding for image classification. We use encode decode for text-to-text translation. We use a modification of encode decode for question and answer, chatbots, all kinds of stuff. Speech recognition, we can use the structure of speech to make our problem easier, and we can do speech synthesis. So we have our happy, this is a very realistic diagram of what we want to do with deep learning right here. Somebody either speaking or typing a language, communicating with someone else, language agnostic. So, future directions. Where is the research going? We've done a lot of work with attention. So the network can also learn to look at something and decide what's important. So that caption at the bottom of the image was generated by a neural network by looking at the giraffe. And the underline there says that when the network is looking at trees, the white bits are what the network thinks are trees. Note that it is ignoring the giraffe. So it's learned the concept of a giraffe and the concept of trees just from pairs of images and text. Really weird, really cool. Dedicated memory. So people are starting to do things like implement stacks and queues and all kinds of like computer science type stuff, separate from the neural network itself. This is very similar to memory, but you'll probably be reading and hearing about papers that are moving memory out and talking about Turing machines and things like that. So one of the other big papers that came out was a neural network that can play Atari games on its own. So one of the big things that's going on recently is trying to tie together this really complicated piece of machinery that can learn abstract representations of stuff with something that understands how to make decisions with some kind of policy. So basically they said, here's input game stuff. Here is the buttons you can possibly play, maximize your score. And they ran it for a really, really long time, and at the end, they had something that plays Atari. And I'm not gonna show this video here due to time, but I highly advise you to click on it and then think about if you could play Breakout better than that. My answer is absolutely not. So, takeaways and opinion time. We could use deep learning like you would normally approach graphical modeling, and the following talks may immediately say, no, we wildly disagree with Kyle, and that's okay. They're different tools, but it's the same conceptual idea. We have knowledge of the data that we're processing, and we want to encode that somewhere. You might encode that in the features that you get. You might calculate for speech something like a Mel frequency substral coefficient that captures the dynamics of speech in a particular range. Or you could encode that in the network itself and just process raw data and find out what features you learn naturally. Conditional probability modeling, in my opinion, is the key to doing deep learning at a high level. You can put knowledge in the model structures, not in the features. Let the features be learned from the data, and you can also use conditioning to add controls or to constrain the solutions you get. So, that's it. It was fast. It was rough and ready. If you have any questions, I'm around at the conference afterwards. Here's a bunch of links and slides to Theano code that does a lot of this stuff. And if you want to recreate the diagrams I showed with the digits, I'll have that code available in my GitHub repo as soon as I sit down. Thank you. We have 3 minutes, so you can breathe.
Short questions. A couple short questions for Kyle.
Fantastic.
Oh, we got one.
Oh, question.
Do you think there's any promise for using neural networks for traditional social science type problems? You see a lot of text image, like what's called unstructured data, but really has structure.
So it depends on what your goal is in your particular scientific study. Yeah, so the question was, do you think there's an option to use these kinds of neural networks for things in the social sciences? So if your goal is pure classification, plain and simple, absolutely. If you have a lot of data and you want to do classification, neural nets are a great way to go. If your goal is to introspect what you've learned about the data and make some fundamental hypothesis about social interaction, maybe not. And that's the introspection piece of the automation spectrum. Yes, and so when I say a lot of data, we're talking on the order of terabytes-ish for some of these big problems.
One more in the back.
Yeah. Those of us who haven't dabbled in deep learning much yet, if we wanted to try to solve a deep learning problem within our organization in a time scale of like 6 months, is that reasonable for someone who hasn't delved into it, or do we need a deep learning person?
So the question was, if we want to try to solve a problem in our organization without delving deeply into deep learning in approximately 6 months, is it plausible? Absolutely, depending on the complexity of the problem you're trying to solve. If you're trying to make classifications better or even process images, there's a huge bevy of resources out there and a lot of people and a lot of pre-built stuff to just do this. If you're trying to push to the edge and learn to play, I don't know, Super Mario on the NES or something, maybe not. But definitely for classification and specifically image or text classification, absolutely.